quantum no signaling bicorrelations and quantum automorphisms graphs.
Thank you very much. And I just want to express my gratitude to the organizers for running such a great conference. It's my first time at ICMS and it's been really great. Yeah, so I want to talk a little bit about some joint work with Sam Harris, who's at Northern Arizona University, Todorov, and one of the organizers, and Ludmila Turovska. And she is here as well. So I guess most people know these people. Okay, so yeah, what's the kind of purpose of this talk? It's to talk about quantum input, quantum output games, or at least an instance of these, and in fact a motivating example of these things. But I want to sort of think about this setup maybe from a slightly different angle. And this is really thinking about, I want to look at graph isomorphism. From sort of two perspectives. One is a quantum input, quantum output, non-local game perspective. And very much related is really thinking about graph isomorphism from the perspective of operator systems, in particular graph operator systems. Okay, so yeah, let me just start off nice and slow since it was the last day and perhaps we're all a little tired. So in this talk, G1 and G2, these are just going to be finite simple graphs. Okay, so finite vertex set V1, edge set E1, G2, B2, E2. Okay, these are graphs. And let's assume, to simplify things a little bit, that these two graphs have the same number of vertices. Okay, and generally, what we're interested in is the situation of whether or not these two graphs are isomorphic. So we say there's an isomorphism. Right? So we have an isomorphism. G1 is isomorphic to G2. Of course, if there exists a bijection, phi from vertices from G1 to vertices on G2, okay, such that it precisely preserves the edge relation. Okay, so that is if, let's say, x, y are in E1, that happens if and only if phi of x, phi of y are in E2. Okay, so yeah, this is of course the usual notion of isomorphism between two graphs. Essentially, if you identify the vertex, well, if you think of the the vertices as labeled 1 through n, there's essentially a permutation of the vertices, which turns the edge set of one graph. Okay, so these are really the notion of two graphs being the same, and so what I want to do is sort of recast this notion in the language of the graph operator systems to start. So remember, we've maybe seen this a few times, alluded to in Roy's talk and also Ryanga's talk. Right, so if G is a graph, right, with n vertices, then there's a natural space of matrices you can associate to G, right? So you associate it to G is this set SG, which is the collection, well, it's going to be some subset of matrices in Mn. Okay, so the canonical basis of C to the n will be thought of as, you know, the labels for the for the vertices, and then we look at all matrix units, E, X, Y. I don't want to take the span, of course, to define a linear space. Complex linear span of all matrix units, E, X, Y, such that X, Y is an edge, or X equals Y. All right. So, yeah. So this is the graph operator system associated to our graph G. Okay. So you can, of course, just directly translate the situation of an isomorphism between two graphs in the language of operator systems, in the language of these graph operator systems. So now, if we go back to these G1 and G2, right? And suppose they're isomorphic via some fixed isomorphism phi, then of course from phi you can really think of, because phi is a permutation of points, you can associate to phi a permutation matrix, right? So you can get a permutation matrix from this, and of course this is just going to be, so this is a matrix indexed by vertices x in V1, vertices A in V2, okay? And of course it's going to be, UXA is going to be 1 if y inverse of A is equal to x, and 0 else, right? So, you know, the usual just identification of a permutation with a permutation matrix. Okay, and then a little calculation gives, well, you have now SG1 and SG2, and if you take your permutation matrix, you can conjugate and get this relationship. Okay? So SG1 is unitarily conjugate to SG2 via a very specific permutation matrix. Okay? So what does this mean, of course? If I want to sort of push graph theory into the world of operator systems, this is really saying, in particular, that SG1 and SG2, these are two operator systems in Mn. These are completely order isomorphic. Which I'll just denote by COI. Okay? So, of course, it's a very special type of complete order isomorphism. And, you know, so you have a very special type of unitary which conjugates SG1 into SG2. And of course, for operator systems, complete order isomorphisms can be a lot more interesting than just, you know, sort of spatially implemented unitary conjugations. So it's natural to ask, you know, so when you go from graphs to graph operator systems, you're sort of going from one category into another. And sort of the notion of isomorphism on the level of operator systems is complete order isomorphism. And so you could ask yourself whether or not complete order isomorphism of SG1 and SG2, just in the abstract sense of complete order isomorphism. So that really means, just for those who haven't seen this before, you have a unital completely positive map. So maybe you would call this a unital complete order isomorphism from this one to this one, which is invertible, and whose inverse is completely positive as well. Okay. So it's really the notion of isomorphism at the level of operator systems. Okay, and then quite interestingly, there's a very nice theorem due to Carlos Ortiz and Vern Paulson, which really says that actually, if you take a graph operator system and you throw away, you just forget that it's a graph operator system. You just think of it as an operator system. You have two such things living in the same matrix algebra, then actually complete order isomorphism is equivalent to the original graphs being isomorphic. Okay, so let me say the following. The following are equivalent for our graphs G1 and G2, which is 1. These graph operator systems are completely order isomorphic. 2, there exists a unitary matrix, not necessarily a permutation matrix, which conjugates S1 into S2. And then 3, of course, graphs 1 and graph 2 are isomorphic as graphs. So this is kind of an amazing result in a way, because here, I mean, if you look at 1 and 2, it's not a priori clear that from this information one can actually cook up an honest permutation of the vertices of the graphs, which implements an isomorphism, right? So, you know, of course, 3 implies 2 implies 1, and the question is whether 1 implies 3. And yeah, so this is a very nice theorem. Yeah, and the tools that kind of go into this are really understanding the structure of the C-star envelope of these operator systems, SG1 and SG2, okay, for graph. Okay, yeah, so this is sort of the setup of this talk. And what's the kind of, what's my reason? So what does this have to do with quantum input, quantum output games? Is really, I want to look at this relation here in particular, which is equivalent to graph isomorphism. Okay. So I have two graphs and their associated operator systems, and I look at their operator systems, and I can find a unitary which conjugates one into the other. I want to try and interpret this this relation here in the language of graph isomorphism games. Okay. And in some sense, I want to see this sort of fuzzy version of isomorphism of the graphs. Of course, an honest isomorphism should be coming from a permutation. This to allowing general unitaries. Sort of what kind of deterministic strategies for what kind of game give rise to this actual notion of isomorphism, which in turn is equivalent to isomorphism of the ordinary graphs. Okay, so as one might expect, permutations correspond to functions, so they should somehow correspond to deterministic local strategies for a finite input, finite output type of game. All right, and then when you're using general unitaries, you should somehow think about quantum input and quantum output games, and this should be somehow witnessing the existence of a perfect local strategy for an isomorphism game where we maybe relax the inputs and outputs to be quantum states. Okay, so that's the sort of direction I want to go in. And maybe let me just remind us of what the graph isomorphism game is. Okay. So the graph isomorphism game so again, I have these two graphs, G1 and G2, and I want to talk about a non-local game associated to G1 and G2. Well, so for this, I need an input set So Alice and Bob are going to have the same input set, and this will be the vertices of G1. The output set for this game is going to be all of the vertices of V2. Okay. So if you look at the description of the graph isomorphism game in the literature, there are relaxed assumptions where the graphs maybe don't have the same number of vertices. In that case, one has to be a little bit more careful about how the game is defined. But here I'm restricting to the situation where we know the graphs are the same size in terms of numbers of vertices. Okay. And so normally we would specify a distribution on the questions, so V1 cross V1. For this, we'll just, let's say, assume we have the uniform distribution, okay, in general. So I will kind of ignore the probabilities on the referee's question set. But anyways, so what are the rules of this game? So somehow you want to think about the players, Alice and Bob. Right, and what's going to happen is Alice and Bob will receive questions, which will be vertices in V1, and they will respond with answers, which will be vertices A and B from V2. Okay. Right, and then the winning criteria. So the rule function lambda AB xy is 1. Okay, so somehow we want to be checking whether, in a sense, the players are sort of implementing an isomorphism between G1 and G2. So the way you should think about this is in terms of the relation on the inputs versus the relation on the outputs. So we want to check that the relatedness is preserved with inputs and outputs. Okay. So here, relation. So for a graph, the relation or relatedness of let's say vertices x and y, this is given by a 3-valued function, plus 1 if x is equivalent to y, 0 if x is not equivalent to y, and x is not equal to y. Okay, and then -1 if x equals y. Yeah, okay. So the condition in order to win a round of this game is simply that, if Alice and Bob receive the same answers, or sorry, same questions, then they have to reply with the same answers. If they reply with the same answers, they should have received the same questions. So this is a bisynchronous game, as Vern described a couple days ago. And the other thing is that you should be edges on one side if and only if you're an edge on the other side. Okay. So this really is kind of in the language of two-player interactive protocols, sort of the capturing the essence of graph isomorphism. Yeah. All right. Yeah, so this is, yeah. Setup. And, right. Now, yeah, so I want to consider perfect strategies, right? So perfect strategies for this game, given that we have, let's say, a probability distribution on the question set with full support, perfect strategies are, of course, correlations. Right, so such that you have a losing input-output pair. Okay. Oh, 0. Yeah. So these would be perfect strategies. Right. So, yeah. So what is clear from, if you look at this definition, this is going to have to be a, well, in general, we will assume it's a no signaling correlation. And bisynchronous. So the perfect strategy condition implies this is a bisynchronous correlation. Okay? And then you can ask, what do QC correlations look like? And this was also alluded to in Bert's talk. So perfect QC strategies, right? This is related to the notion of a magic unitary or magic permutation matrix, or quantum permutation matrix. These go by several names. So recall, definition, a magic unitary let's say U in Mn of A, okay, which will be a matrix with entries UXA, sort of indexed by the appropriate sets. Yeah, so this is where A, let's say, is a unital C-star algebra. Is a unitary matrix in this C-star algebra, Mn of A. And then the conditions we will impose are essentially you're replacing permutation matrices with operator-valued permutation matrices. And what does that mean? You replace 0, 1 entries with general operators, which are self-adjoint projections, and the rows and columns sum to 1. So sum over A, UXA equals 1, and that's the same for sum over X of UXA. Okay, and this is true for, of course, all rows and all columns. So magic unitary is one of these objects. And yeah, keep that. Okay. Okay, and of course, one thing can ask, so we know that QC bisynchronous correlations by results of Rahman and Vern Paulson tell us that in the QC model, bisynchronous correlations are exactly of the form PAB given XY, given by tau of UXA UYB. Okay, so, and what is, so U is a magic unitary, and A tau is a tracial C-star algebra. Sorry about the tiny writing. So this is giving us a direct link between bisynchronous correlations and traces on essentially the universal C-star algebra associated to these relations here. Okay, and then you can ask, what else do you get when you have, of course, perfect strategies for the graph isomorphism game? And in a sense, you get an analog of this statement here. Okay, so theorem. So this is a paper by Atsarius, Samal, Nijinsky, Roberson, Samal, Severini, and Varvitsiotis. Where this is this paper really that introduced the concept of a non-local game capturing the notion of graph isomorphism. All right, and what they have is has a perfect, so this isn't the complete formulation of what they prove, but one, a perfect QC strategy. Yeah. If and only if there exists a tracial C-star algebra, a tau, such that, and a magic unitary over A, such that U star SG1 tensor 1 U is contained in SG2 tensor A. And of course, when you have operator coefficients, this is not quite enough. Turns out you need essentially the symmetrized version of this as well. Okay, and I'll write it this way: U bar times SG2 tensor 1 U transpose is contained in SG1 tensor A. So in their paper, it wasn't phrased in the language of operator systems, but this is it was instead phrased in terms of adjacency matrices of graphs. But one can use the sort of algebraic relations in quantum permutation matrices in much the same way as you would essentially prove this result down here for ordinary permutation matrices.
Tensor A, or is it tensor 1 on the right?
On the right, it is tensor A. Yeah. Yeah, in a way you can kind of think about, in a sense, this is like, you know, a conjugation from one into the other, but now you allow operator coefficients in your map. Yeah. Okay.
May I ask a question?
Yeah.
In the Ortiz-Paulson theorem, you somehow lose the magic, right? I mean, that
Yeah.
U doesn't have to be magic anymore.
Yeah.
Is there any analog in that context where, you know, you replace there you need some magic
Yeah.
unitary where you can something from non-magic unitary and it's still okay, or is that?
So, I mean, this is an open question, yeah. And essentially, one can now, look at quantum isomorphism of graphs in this language of non-local games, and you see that, again, it's a conjugation relation at the level of operator systems, sort of, but now with operator coefficients. You can ask yourself, you know what? Again, so this is sort of like a matricial or operator valued version of this inclusion or equality there. And you can ask then, you know, what happens if I replace this by, you know, operator unitary matrices? Okay. And essentially, yeah, this is sort of the motivation in a sense for this talk. And again, these will be perfect strategies for graph isomorphism game, but now viewed as a quantum input, quantum output game. So in the language of quantum graphs, I know some people are fans and some people maybe not so much, but in the language of quantum graphs, what this really is you have SG, and carried with that is some data of this vertex set, which is really a bimodule property of SG with respect to the diagonal subalgebra. But you can forget about the bimodule structure of SG and just think of it as an operator system in MN. And now, in the language of quantum graphs, this is a quantum graph over MN. Right? So you're just allowing your vertices to be quantum in a certain sense, and this is really a natural thing to do from the perspective of zero error communication problems and stuff like that. But you know, just from that sort of perspective, you sort of forget about the bimodule structure. Then it really, in a sense, doesn't necessarily make sense to just restrict yourself to the special class of operator unitary. So that's sort of the motivating point here. Yeah, so perfect QC strategies look like that.
Mike, the question.
Oh, yeah, sorry.
Clarification question.
Yeah.
On the definition of this magic unitary,
Yeah.
there's a line UXA
Yeah.
equals to UXA adjoint.
Yeah.
And then
Oh,
equals to
yes, I.
The square
Thanks.
missing. Projections.
It's yes, that's right. So I meant to write squared. Yeah, good. Yeah. Okay. Right. Maybe I'll. Here. So. So yeah, this is again, you know, quote QC strategies, and of course there's an analog for Q strategies, QA, all this stuff. But what I want to focus maybe on is in the local situation. Again, it's just ordinary graph isomorphism as one would expect, right? So to the loc situation, so we have a perfect loc strategy if and only if. The same thing is true. You don't need to write the two equations anymore because, well, maybe I'll write it this way. Right here where U is a permutation matrix. Yeah. So deterministic local strategies. So in general, a local strategy will still be probabilistic in terms of the correlation, which in a sense just means it will be somehow implemented by a mixture of these deterministic conjugations by permutation matrices. And now, yeah. So again, so the point here is to really think about, yeah. So what would it mean, sort of operationally, to allow this situation, and also for the, you know, quantum situation as well. Okay. So. Right. So in other words, yeah. So again, this is really just, you know, again, local strategies should somehow correspond to, you know, the ordinary notion of isomorphism, and it is exactly that, where this is a permutation matrix. Yeah. So so I want to think about this graph isomorphism game from G1 to G2 now as a quantum input. So Jason, I guess it was on Monday, introduced this concept of quantum input and quantum output, no signaling correlations in games and things like that. So hopefully some of this will be familiar, but let's just, I guess, take it slow here. So first thing is, you know, I'm going to do really what I said earlier, which is I'm going to think of a quantum graph, like so SG1, let's say, really as now sort of just think of it as a space of matrices, okay? So SG is really some subspace of Mn, and of course you can identify Mn in various ways with really you know, C to the n tensor C to the n. Okay? So I want to think of then, you know, really SG as somehow corresponding to some subspace of a bipartite system where I'm really, you know, I mean, I can just think of it as a space of matrices or some space of bipartite, subspace of a bipartite system. And really what I'm doing here is I'm just totally forgetting now where the graph came from. And the data of this graph is now really encoded in the essentially range projection associated to UG. Okay, so this is just a subspace, linear subspace. Okay, so PU G. Okay, and now if I have G1 and G2, right, I'll just call this P1. Okay, and this is the projection onto U, G1. Okay. All right. So now when you think about you know, inputs and outputs for the game, really what they are is certain, classically, they're going to be classical states viewed as quantum states on this system here, right? The inputs are ordered pairs, which in general will be probabilistic mixtures of ordered pairs, so classical densities with respect to some fixed basis, and in general, one could allow general quantum densities on this space. Okay.
But that UG is not a unitary, right? I mean,
No, this is just the
a
notation is
subspace
probably
or
yeah.
whatever, right? I mean,
So really, just think of it as SG, interpreted as an Okay, so right. Yeah, so really what I want to do is I want to think about quantum correlations, bipartite quantum correlations from this space, from this bipartite system to another copy of the same system, right? Okay. So I want to consider, no signaling, quantum correlations. All right. And where am I looking? So let's say, just to distinguish inputs and outputs, maybe I'll write X and A, just two finite sets of size n. Okay, and I want to consider channels, bipartite channels from MX tensor MX into MA tensor MA. Okay. So these are channels, quantum channels. Okay. So again, classically, a correlation, a bipartite correlation, is just an ordinary noisy bipartite channel from the diagonals on X, tensor diagonals on X to diagonals on A, tensor diagonals on A. Okay. So these are quantum channels. All right. And the no signaling condition was introduced by Jason. And no signaling really means, again, we have well-defined marginals. Okay. So what this means is if I, let's say, take an input rho x tensor rho x prime, okay, and I look at the output, and I trace out Bob's side, or Bob's output side, okay, this should be equal to one tensor trace of gamma rho x prime, okay, for any states. Rho x prime, and rho prime prime. Yeah. Okay. So that is, in this case, this will be Alice's marginal. It does not depend on Bob's input. And there will be, of course, the symmetric version of this for the other side for Bob's marginal. Okay. So same for Bob, and I won't write that down. So these are no signaling quantum input, quantum output correlations. And essentially what I want to do is I want to think about these as somehow more general strategies for the graph isomorphism game, where now, my graph operator system is somehow related to densities or supported on certain densities here, and the other one is on densities over here. Okay? Densities supported on that system. Yeah. Right. So, so these are quantum input, quantum output correlations. So these were introduced by Duan and I think Winter. Right. So. So in general, of course, what are QC correlations in this such setup? So quantum commuting model bipartite, no signaling correlations. These really correspond to operator stochastic matrices. And these, okay, these maybe seem a little scary when you first see them, but they are really just a rephrasing of the notion of POVM, but now where your input space and output spaces are matrix spaces instead of just finite classical input and output spaces.
So this here are the strategies which you want to
Yes,
apply,
exactly.
right?
So this is.
So now you want to tell us which strategy is winning.
Yeah, exactly. Yeah. So, yeah. So these things, yeah, these really correspond to, you know, you have a Hilbert space, a state, okay, and then a pair of big ugly matrices with respect to a basis. Look like this, and so where do they live? So this will be in matrices over X, matrices over A, tensor sum B of H, right? And same here. Okay, so these are just some matrices, and I want to think of these as, you know, exactly corresponding to the notion of a POVM, right? For Alice and for Bob. Okay, so the conditions we require, of course, are that the entries of F and E commute, right? So okay, so anything, you know, any subscripts, like so the coordinates of these giant matrices commute. Okay. And now so then, so yeah, so what is a stochastic operator matrix or operator stochastic matrix? The best way to think about it is, again, using the language of how you would think of a POVM dually as a unital completely positive map, going from outputs to inputs. Yeah. So what I mean here is I want to think about E really as corresponding to a map. Let's say, I don't know, alpha E from MA into MX tensor B of H. Right? And the map is, of course, given by E A prime goes to sum over all X prime, EX, X prime tensor, the coefficients, right, the labels. Okay, and I'm going to ask that this just be a UCP map. So again, in the case of usual ordinary, you know, classical input, classical outputs, these are diagonals of size X, diagonals of size A, and a UCP map from DA into MX tensor B of H. This is just another way to tell you what a POVM is, yeah, or a family of POVMs, more precisely. Oh no, just a POVM. Okay. Yeah. So for every, yeah. So essentially UCP map from one space into the other, yeah, with operator coefficients. Okay, and same for F. We can do this, and then it turns out, you know, what do the correlations look like? Right. So gamma is from here to here, and so then you know, really, if you want to specify things in terms of matrix units, let's say, with respect to a basis, right? So I want to look at this thing, and maybe we can just check the coordinate of this. So pair it with, let's say, EA, A prime, tensor EB, B prime, right? So this thing should be the, you know, the analog of really this PAB given XY, right, for an ordinary correlation, right? So the channel associated with the correlation is, you know, has these as its coordinates, as a matrix transformation. And as a matrix, these are the coordinates, and this is just going to be given by pairing with the state psi, you know, E, X, X prime, A prime, F, X, sorry, Y, Y prime, B, B prime. So when you look at it this way, you know, it really sort of, at least intuitively, has some, you know, visual cues that sort of connect you back to the, you know, usual way you would use these systems of POVMs to define an ordinary correlation. Okay, so that's all good. Now, I want to say something about bicorrelations. And how they should somehow be interpreted as analogs of bisynchronous correlations.
So now we have defined some matrix valued correlation. What is the winning condition?
Yeah. So, yeah, maybe let's say that first, actually. So you somehow want, so for, you know, let's say, now I'm going to think of these as just general subspaces, U1 and U2. So UI is just some subspace inside of them, N, or sorry, Cn, tensor Cn. So U1 and U2. Okay. And of course these A and N, or A and X are just labels which are of the same size. Okay, so what do you want to happen? Okay, so somehow, let me just say it this way, since time is of the essence. What would if you were to define this game, what would the perfect correlations be for this? So what do you want? So you would like somehow inputs will be states rho, which will be densities on C to the x tensor C to the x. Okay. The outputs will be states on the range space. Okay. Sort of a strategy for this game will then correspond to a choice of a correlation. Let's say a QC correlation from MX tensor MX into MA tensor MA. Okay, so some channel. And what does it mean to, so gamma of an input will be the output. Okay, what does it mean to sort of satisfy the natural winning conditions for this game? So one, to win.
Excuse me, D here doesn't mean diagonal, it means state, doesn't it?
Yes, yes, yeah, D. Yeah, good. Okay, so to win, of course, remember, associated to these subspaces are the corresponding orthogonal projections P1 and P2, right? On the corresponding tensor spaces. So, of course, what you want is an analog of a graph homomorphism at least, right? Going each way. Okay. All right, so yeah, so what you're going to want is, so if the supportive row is contained in P1, then of course you're going to want the support of, that's a row there, gamma of row contained in P2. All right. And similarly, okay, you'd also want to have some sort of notion of invertibility in the sense that, okay, you would like to possibly know what happens if the output side is supported, you have a density supported on the other side, and here we insist that this is somehow not quite satisfactory, but we have to insist here that these correlations be actually bistochastic. This actually follows sort of axiomatically in the classical case, and it's not clear whether one is making necessarily the most general assumptions here, but gamma bistochastic means that the dual map, which is a priori just uniformly completely positive, this is also going to be no signaling, and yeah, a channel. And you're going to ask that, of course, if you have some sigma supported in P2, then gamma star of sigma has support in P1. So the support of it.
So if you're not bistochastic, can't you just assume that if the support is contained in the orthogonal complement of P1, then you get into the orthogonal complement? Because that's the same in the bistochastic case, right?
Yes, yes, I guess that's true.
If the supremum of rho, if the support of rho is contained.
Basically,
Okay. Yes, I suppose you could rephrase it in terms of just the support of the dual map. But in any case, in order to get a nice analog of anything like this, it turns out we need to make assumptions on our strategies that guarantee that the dual map is already non-signaling correlation. Okay. All right, and in the QC model, okay, something nice happens. One gets an analog of this. But there's one additional thing. What does bisynchronicity mean here? Okay. In the quantum case, this turns out to naturally be corresponding to a notion called biconcurrent, or rather concurrent. I can just say concurrent. Okay, and so this really is an additional assumption we will impose. And that is if I take Jx to be the maximally entangled state, okay, in the input space, then, well, we know the output is going to have to be a rank 1, well, not necessarily rank 1, but it's going to actually be equal to the corresponding maximally entangled state here. Okay, so we're going to impose this assumption. And this is, perhaps when you see this, it's maybe not so clear of a analog of bisynchronicity, but one way to think of this is, you know, if you have bipartite inputs, what does it mean to send Alice and Bob the same thing in the case of quantum inputs, right? That is really you're sort of sending them two legs of a perfectly correlated, you know, maximally entangled pair, and you know, if you measure the behavior, the output, it should still maintain this sort of perfect correlation. So it's this sort of notion of same inputs should result in the same outputs. Okay. Another sort of algebraic reason for this is, you know, if you look at more general systems like mixed classical quantum systems, that's of course looking at multi-matrix algebras. If you look at essentially what is J of x in this case, J of x is really the dual of the multiplication map applied to the unit of the algebra, if you think of your multi-matrix algebra there. And classically, that really is the projection supported on the diagonal. Okay, in that case, you won't have a rank 1 projection, but in that case, synchronicity is really saying your channel has to somehow be supported inside the same object on the other side. Okay, in the fully quantum case, there's only one choice. It has to perfectly ascend this to that. If it's sort of contained in the support of this, it's going to have to be equal because of the rank considerations. Okay, anyway, so this is concurrency, so it's kind of like an analog of synchronicity. And in the bistochastic channel case, the symmetric thing is true, so the dual will have the same property. Okay? So it's sort of like bisynchronous automatically. Okay, so let me just end now with just saying what you can get in the QC model. So in the QC model, you get an analog of Paulson-Rahman, which is really, you can replace magic unitaries with general quantum biunitaries. So a biunitary. A biunitary is U, given by UXA, indexed by the same stuff in Mn of A. Okay, but now I'm just imposing that it's a unitary. Okay, so U is unitary, and it turns out, for subtle reasons, the transpose of U also should be unitary. So this is where the notion of biunitary comes from. For magic unitaries, of course, this is automatically true. The transpose is the inverse in that case, but in general, of course, this is not true. In a nice calculation, if you're familiar with Brown's universal non-commutative unitary algebra, his algebra is the universal algebra with these relations without this, and it turns out this is not an automatic relation when you consider non-commutative entries. Okay, so in other words, let me just say, so in this setup where you have bicorrelations which are concurrent, the QC model becomes a lot simpler. You have a trace on A, okay, and really, just think of it this way. Yeah, you can take right here. What is this in that case? So in general, you have this thing. Okay, so you have a pair of local stochastic operator matrices, but now actually you can take E x x prime, A prime to be U x A star, U x prime A prime. So that's an example of a operator stochastic matrix, and turns out for a biunitary. In fact, it has more properties. Okay, and trace implements essentially, the usual thing. So this is going to be, in this case, equal to the trace of U x A star U x prime A prime. And then the F is replaced by the E stars, as you expect, with these synchronous correlations. So you're going to get U y prime B prime star U x y. So somehow you should think of this as like what's replacing the part of the magic unitary in the classical case, and this is the other part. So this is like the UXA in the quantum case, and this is the UYB in the quantum case. You have like doubly many indices. And let me just finish then by saying how. Whoa, sorry, I'll break this place. Okay, so let me just finish by saying this. What does it mean in terms of these? It really means, so local strategies really correspond to where now U is unitary, okay, or mixtures of these, okay, And the QC strategies in this case really correspond to what we had before, U star SG tensor 1, U contained in SG2 tensor A. Okay, and similarly, for the other side, U bar SG2 tensor 1, U transpose is contained in SG1 tensor A. Okay? So in other words, Marius, the answer to your question is, if you allow bicorrelations, which are concurrent,